Hi students, welcome back. Today we are going to look at time-based key value store problem on LeetCode. So let's look at the problem statement first. So the problem statement says we have to design a time-based key value data structure that can store multiple values for the same key at different timestamps and retrieve the key values at a certain timestamp. Okay, so we have not just a simple map with key value, but map with key value and a timestamp. So a key can have multiple values, and each value comes with a timestamp. We have to implement a time map class, which stores this key and gets the key for a timestamp. Okay, when you get the key, okay, if the value at the given timestamp is not found, then we have to find the lowest closer timestamp of that. Okay. If there are multiple such values associated with the largest time previous. And if there are no such values, we simply return empty string. So the important thing is for a key, there can be multiple values. Each value has an associated timestamp. Okay. And when we are getting a key for a timestamp, if a value for that particular timestamp is not possible, we pick up the lowest closer of that timestamp. Let's look at it through an example. Okay, so this is the given example. So these are the operations that are happening. Okay, okay, let's say these are the operations that we have. So what we are saying is, okay, we have a new time map. So we are creating a time map. So let's think of it as a key value store. Okay. So we have a key value store to start with. Okay. Initially, what we are doing, our first uh, step is set foo bar 1. So we are setting at foo a value bar and 1. 1 is the timestamp. Okay. Now we are saying get foo 1. So we are getting this value which is foo and timestamp 1. So we should return bar. No ambiguity there. Now the next operation is get foo 3. Okay. When you are trying to get 3, there is no 3 in our map. So what we will do is the lowest closure, which is 1 in this case. So we will again return bar. Okay. Now the next operation is set foo bar to 4. So foo has another value called bar 2 and at timestamp 4. Okay. We store the, we are just storing it. Now get foo 4. When you are trying to get the value of foo at value 4, you have the exact same value. So you will return bar 2. Now, when you are doing get foo 5, you don't have a value at timestamp 5, but you have to return the lowest closure, which is why it would be again bar 2. Lowest closure of 5 is 4. Okay. So, if you closely observe here, let's look at the constraints that are given as well. Okay. What they are saying is all the timestamps are in strictly increasing order. So we get the timestamps in a sorted order. Okay. And we have to find the value. So here in this example, the timestamps we got are 1 and 4. Okay. So in the first case, we were in the first get, we were searching for 1, we found it. In the second case, we were searching for 3, we didn't get it, but we had to return 1. In the third case, we were searching for 4, 4 was available. Next, we were searching for 5, 5 was not available, but we had to return the lowest possible value. So you are basically doing a binary search on a sorted timestamp value, which we can easily use a modification of a binary search. Okay, so let's run some simulations and see how binary search behaves, or how the values are when you don't find the value. Okay, so there is a simulation available. We will just run that. First, let's just say this is the array that we have. Okay, 0 to 31 elements. Let's say we are looking for element 460. It is at index 9. Let's run the binary search. Okay, so when it is available, our mid will have the value and we will return the index. Let's say we are looking for something higher and which is not available. Okay, 465. Let's say we are looking for 465. Now let's see what happens to close the low and high values. Okay, so we stop the binary search when start moves beyond end. If you clearly observe the end or the high value, it is at 460. Okay, we were looking for 465. So 460 is the lowest closer of the value we wanted, and end is pointing there. Okay, let's run another simulation. Let's say we are looking for 450. Let's see what happens now. Okay. Again, end is at 8, which is 440. 440 is the lowest closer for 450. So at any time, end or high is having the lowest closure value of the given search element. Let's say we are looking for something which is not even available. Let's say we are looking for 50, not even in the range. Now let's see what happens to high. Okay. Now high went beyond the array. Okay. So there are no elements. So there is no lowest closure of 51 in this case, which is why high went to beyond the array. Okay. Now let's say we are searching for 950. Okay. I'm just trying to cover all the boundary cases. I'll give this link in the description. You can try the simulation yourself later too. Okay. Now if you see, high is at 31, which is again the lowest closer. Now, low went beyond the array, which is 32. 32 doesn't exist. Okay. So, at any point, whether it is in the end of the array, middle of the array, greater, lesser, high is always having the lowest closure if we don't find the element. So, we will use the same property and we will do our code. So, what we will do is we will um, store the elements in a map, obviously with the key, and the value of it would be list of time and value, just like how we did here. It will be list of time and value. Okay, and since the elements are coming in a sorted order, or the timestamp is coming in a sorted order, we already have that list sorted. So what we will do is we will just do a binary search on it and we will find the element. Okay, so first we need a data structure to hold the time and value. Okay, let's define that. Let's call this a simple time value. Okay, okay, it has timestamp and value. Let's initialize it. Okay, what we are saying. Okay, now we have the data structure. Next, what we will do is we will use this new data structure in a map. So ultimately, what we want is a map. Okay, it's a simple hash map, but the key is string and the value is list of time values which we just define. Okay. Now, when we set it, we have to look for if the value already exists and all that. So, what we will do is we will check first if the value, if there is a list already defined at that value. So, we will use the maps get or default. So, if there is a array list already available for this key, we will get that. Otherwise, we will create a new array list. And to that, we will add the current value. So we will create a new time value with the given things and we will add it. Now, we will put the new list back in the map. We have to put it back because sometimes we are creating a new one. Otherwise, by reference it will have the values, but since we are creating a new one for the first time, we have to put the value, otherwise the map will never have the values. So this will complete our set. So what we are doing is we are checking if a value exists at the key. If it doesn't exist, we are creating a new array list. To that list we are adding the value and timestamp and we are putting it in the map. Now we have all the values in the time map, keyed by key and a list of time values in a sorted fashion. Okay. Now we have to get it. Okay. To get it, first we have to check if a value exists at the key. So that is simple. In the time map, we just get for that value, and if a value exists for this key, okay, we will get the array list for that key. If it doesn't exist, we will get a null. So if it is null, that means when there is nothing to return, we have to return a empty list. So we will return empty. Okay. Now we know that a value exists and we have to look for this timestamp in that array list, in that sorted array list. So like we said, we will use binary search for this. So for binary search, we need a start and an end. Okay. We are starting at start of the array and end is at the end of the array. So how long do we do the binary search? Well, start is less than or equal to end. And what do we do? First we get the mid. We have already done a binary search problem before and we already discussed why we do like this instead of start plus end by 2. That is to avoid the integer overflow. You can look at uh, look at that video once. Oh, I accidentally submitted. That's okay. Let's continue. Now we have the mid value. Okay. Mid index. Okay. Now let's get the time value at this mid index. So from the array, we are getting the time value of it. And in this case, we have to do a comparison by timestamp. Okay. So if mid time value dot timestamp is equal to timestamp, which is the past timestamp. That means we found an exact match. Then we just return mid time value dot value. Okay. So if the timestamp matches, we return the exact value. Okay. If it doesn't match, then we have to decide which side of the array to move. This is again standard binary search. Okay. So if timestamp is greater, we move to the right side. Okay. Otherwise, we move to the left side. Okay. Now, this way we will process the complete sorted array. And if we found a value, we will return that. Otherwise, what we said is end will have the lowest common value. But there is a case where end can go beyond the array. So we have to check for if end is greater than or equal to 0. Only if it is greater than or equal to 0, we use that. Okay. Otherwise, that means we haven't found any value. So we return just a empty list. Okay. Let's run this and see. Okay. Time map is not okay. Okay, so what it is saying is that types doesn't match. Here we use list and there we used array list. That is the reason. Okay, let's run it again. Okay, now it passed. Let's submit this and see. Okay, so it got accepted. So simple thing that we tried is we looked at how the indexes are after the binary search ends, and we used that property to return the lowest possible value. Okay. So this is one nice application of binary search. Binary search will have numerous applications like this. It's very important to understand the binary search properly. Okay. So if you use a tree list tree map data structure within Java, you can do this using inbuilt functions without writing your own binary search. But that's not what is intended. I think you should understand the binary search implementation. Okay, that's all we have for this video. Thanks for watching.